The Cognitive Theory of Multimedia Learning. Hi, I'm Kevin Thorne, graduate student at the University of Memphis. This presentation is for class IDT 7074. Before we talk about multimedia learning, let's take an overview look at how this theory evolved. We'll start with the cognitive theory in general. Then we'll briefly discuss the cognitive learning theory, all of which will build into the cognitive theory of multimedia learning. In cognitive theory, prior knowledge is known as an individual schema, their internal structure of known knowledge, or the stuff I know. In our working memory, it's assumed that we can hold up to about 5 to 9 bits of information at a time, or schemas. Average is about 7. To better illustrate, consider these 6 random letters: D, X, U, R, B, L. Our schemas may recognize each of the letters, but together there is no prior knowledge to draw from. Therefore, we've consumed 6 of our average 7 available schemas to draw from recall, and we're about tapped out at this point. However, if we present these 6 letters in a string, MEMORY, we see these letters as a recognizable word. Memory is a structure of letters that allows us to draw from prior knowledge, a schema. And since the word itself is one schema, we still have available working memory. That's cognitive theory in general. Now, the cognitive learning theory is rooted in the idea that the learner will recall information from prior knowledge, the stuff they already know, those schemas in long-term memory we just referred to. To attain meaningful understanding of new information, the learner then integrates with their schemas and their existing knowledge in long-term memory. Now that we have a baseline for cognitive theory and then cognitive learning theory, we can have a better understanding of multimedia learning. And this is about understanding how a learner's mind works. This understanding will allow instructional designers to design meaningful learning experiences. Now, this theory was first presented by Richard E. Mayer and Roxana Marino in 2003, in part by dual coding theory by Alan Pavio. To understand, this theory follows 3 basic assumptions about what we know about cognitive science. The first assumption is the dual channel assumption. We're thought to process information through 2 channels. One is the auditory channel for processing auditory inputs and verbal languages. The other channel is visual for processing everything we see and pictorial representations. The next assumption is limited capacity that we referred to earlier. Even though our auditory and visual channels are on high input alert, limited capacity assumes we can only process about 5 to 9 bits of information at a time. We mentioned average of 7 earlier. The third assumption is active processing. Now this one is a little bit more involved, suggesting that for active processing to work, both auditory and visual channels must be engaged. This assumes that in multimedia learning there needs to be 5 additional cognitive processes engaged all at the same time for active processing to work, specifically focusing on what we see more than what we hear. The first is visually selecting words from the screen, similar to what you're doing now viewing this presentation. Visually selecting images or photos from the screen, organizing those selected words, organizing those selected images, and finally integrating all those selections and comparing them with our prior knowledge. Whoa, that's a lot of brain power going on just to retain new presented information. Now, Mayer and Moreno developed a model. To help better illustrate how all this works, I've taken the model apart and I'll rebuild it here so we can have a better understanding. It all starts with an online course, e-learning, or some other type of multimedia learning experience. This model represents 2 rows of information processing: the auditory channel and the visual channel, or words and images. The dual channel assumption that we just looked at a moment ago. In order to select words and or images, we need our eyes and our ears, our sensory inputs. Once learners begin processing those inputs from the two channels, they go into working memory. This is where the second assumption of limited capacity is addressed. Learners hear the words of a narrator or even background music that aids in setting the mood and tones of the instructions, and then it goes into what Mayer and Marino referred to in deep working memory as the verbal mental model. Learners also see words on screen as well as any visuals such as images or photos or any other visual representation that is not represented as written language. This is placed in its corresponding channel as the pictorial model in deep working memory, all of which is roaming around inside the learner's working memory. Lastly, in this model is the prior knowledge or the long-term memory. As you can see, multimedia learning consumes a lot of cognitive processing of both channels all at the same time. Working memory has to make representations of what we hear and what we see. Deep working memory is putting all that stuff into mental models. And long-term memory is searching the database of our minds looking for and retrieving relevant known knowledge. My brain is beginning to start to hurt. Now, remember active processing in those 5 cognitive processes of selecting words and images and integrating with prior knowledge? This is all known as essential processing, which is part of the total cognitive demand the learners endure. Words to eyes represent text on screen the learner reads. Words to ears represent spoken words heard by a narrator. Images to eyes represent what images or graphs, etc. the learner sees on screen. And this is when essential processing goes into action into our working memory. Our brains select whether we hear sounds or if we see images, 2 of those cognitive processes in selecting words and selecting images. Then we push these inputs into deep working memory and start organizing everything into mental models, where in the verbal model or in the pictorial model. Organizing words and organizing images is 2 more of those cognitive processes. Remember, for active processing to occur, those 5 cognitive processes need to be engaged. Along with essential processing, learners sometimes may have incidental processing. Incidental processing is those bits of information that may be interesting but have no essential meaning to the learning experience. Now, as instructional designers, we're all guilty of this. Those incidental bits need to be processed and contribute to the overall cognitive demand. Everything up to this point is known as representational holding. Just think how fast all this happens multiple times in a matter of a second. Amazing. Finally, the integration process occurs in this model, representing the merging of all those verbal and pictorial mental models with our prior knowledge. All of it getting mashed together until we process and say to ourselves, here's something relevant that I already knew. Let me mash this with that new stuff. Or, I didn't know that. Let me store that in long-term memory for later use. Cognitive demand is essentially combining all 3 processes. Essential processing plus incidental processing plus representational holding equals the total processing needed, the demand, for learning. Problems occur when we put demand that exceeds the capacity. 3 principles to be aware of are: the capacity for representing words and images is unlimited. The capacity for storing knowledge in long-term memory is unlimited. The capacity for mentally holding words and images in working memory is, however, limited. So, if we know working memory has a limited capacity, then as an instructional designers, we should be conscious of where we place the learner's ability to present information. Otherwise, we are going to do a cognitive overload and exceed the working memory. Now, how do we avoid this? For instructional designers to avoid cognitive overload, a learner's cognitive processing or demand needs to be or is greater than the learner's cognitive capacity. That's cognitive overload. Meaningful learning, however, learner's cognitive capacity, the working memory, is then greater than the learner's cognitive processing or the demand. Basically, too much information plus too many formats all at the same time, you can expect cognitive overload. The solution to reduce cognitive overload in multimedia learning experiences is to spread out the balance of essential processing, minimize incidental processing, and by default, representational holding is not as taxed. Simple, right? If all of this is new to you, replay this presentation a few times and push it into your own long-term memory. Or, if this is all familiar to you and your own prior knowledge is misfiring with what I've shared here, please contact me so I can correct any misinformation. Thanks for watching.